Try to imagine nothing. Go ahead. Close your eyes and try to visualize absolute emptiness. You probably see a black void, maybe some stars in the distance if you're feeling romantic, but essentially you picture a vacuum. You think of space as a stage, a big empty box where stuff happens. You put a planet here, a star there, maybe a confused astronaut floating in the middle. But the space itself, to you, it's just the container. It's the absence of things. I hate to break it to you, but that container doesn't exist. The idea of empty space is the greatest hallucination of the human mind. The universe isn't a box, it's a glob of jello. Okay, maybe not literal lime-flavored gelatin, but physically speaking, you are walking through a medium that is constantly being twisted, squashed, and pulled. When you look at the air in front of you, or the vacuum of space, you aren't looking at nothing. You are looking at a field. And until you understand what a field is, you don't understand physics. You're just memorizing rules for a game you don't know how to play. Let's start with something you can actually touch. Imagine a big, wobbling block of elastic material, a giant cube of jello sitting on a table. Now, suppose I reach in, grab a tiny speck of dirt trapped inside that jello, and I pull it. The jello distorts. It stretches. If you want to describe what happened to that block, you can't just say, it moved. That's lazy. You have to describe how every single point inside that block shifted relative to every other point. We call this strain. If I pull the corner, the middle moves a little, the far side moves barely at all, and the point under my finger moves a lot. To describe this mess, we need numbers, a lot of numbers. For every tiny point in that jello, we need to know how much it stretched sideways, how much it stretched upwards, and how much it stretched forward. And it gets worse. We need to know if it twisted. Did the top slide right while the bottom slid left? That's a shear. Suddenly, this innocent block of jello is a mathematical nightmare. To fully describe the stress and strain inside it, we can't just use a single arrow. We need a concept called a tensor, a beast of a mathematical object that packages all these stretches and twists together. But here's the beautiful part. This isn't just about jello. This is how the entire universe works. Physics is the business of assigning numbers to points in space. That's it. That's the job. If you assign a single number to every point in space, like, say, the temperature, you have what we call a scalar field. Imagine a block of metal that's hot on one side and cold on the other. You can close your eyes and point to any spot inside that metal, and there is a specific number waiting for you, 20 degrees. Move an inch left, 25 degrees. The temperature doesn't jump around randomly. It changes smoothly. It forms a landscape. Now, imagine drawing lines connecting all the points that have the exact same temperature. You get these invisible surfaces, like the contour lines on a topographic map. We call them isotherms. They are imaginary, but they tell you the shape of the heat. But a single number isn't enough for the interesting stuff. Sometimes, the universe has an arrow at every point. Think about a rotating object, or water flowing in a river. At every single point in that river, the water has a speed, but it also has a direction. It's going somewhere. You can't just say, the water is moving at 5 miles per hour. You have to say, 5 miles per hour downstream. This is a vector field. Imagine the room you are sitting in right now. The air seems still, but it isn't. There are tiny currents everywhere. If you could freeze time and attach a tiny little red arrow to every molecule of air showing where it was going, the room would look like a porcupine. That forest of arrows is a field. Heat flow works the same way. Heat doesn't just sit there. It flows from the hot spots to the cold spots. So, superimposed over your map of temperature numbers, there is a map of heat flow arrows. And here is the rule. The heat arrow always points downhill. It wants to get away from the hot zone as fast as possible. Now, we need a way to connect these two things, the temperature numbers and the flow arrows. How do we find out which way the heat will flow just by looking at the temperature map? We use a mathematical machine. We call it del, which is just a fancy name for a symbol that acts like a meat grinder for functions. You feed it the map of temperatures, and it chews it up and spits out a map of arrows. This operation is called the gradient, and it is exactly what it sounds like. If you are standing on a hillside in the pitch dark and you want to know which way is up, you feel around with your feet. You find the direction where the slope is steepest. That direction is the gradient. The gradient of the temperature tells you the direction of the hottest change. It tells you, if you want to get hotter, go that way. And the heat flow? It simply obeys the opposite of the gradient. It runs down the hill. But nature isn't satisfied with just flowing down hills. Sometimes nature likes to spin. Imagine you have a field of arrows that looks like a whirlpool. The arrows aren't flowing out from a center, they are circling around it. If you dropped a leaf in there, it wouldn't just move, it would rotate. To measure this swirliness, we use another operation called the curl. If the gradient measures the slope of the hill, the curl measures how much the field is twisting. It tells you the rotation. And then there's the divergence. This measures how much the stuff is spreading out. If you have a nozzle spraying water, the divergence is high at the nozzle because water is exploding outward. If you have a drain, the divergence is negative because water is vanishing into it. Why am I telling you about hills, swirls, and drains? Because these three concepts, gradient, curl, and divergence, are the language of reality. Maxwell's equations, the laws that govern light, electricity, are just sentences written in this language. They say things like, the divergence of the electric field is the charge. Translation, electric charge is a sprayer that shoots electric field arrows outward. Or, the divergence of the magnetic field is zero. Translation, there are no magnetic sprayers, no magnetic charges. Magnetic lines never start or stop. They just loop forever. Speaking of magnetism, this is where things get really weird. You think you know what magnetism is. You played with magnets as a kid. You know they stick to the fridge and hate each other if you flip them around. But have you ever asked why? Why does a wire carrying an electric current suddenly turn into a magnet? Let's look at the force on a moving charge. We call it the Lorentz force. It's the rule that says if you shoot a charged particle through a magnetic field, it gets pushed sideways. Not forward, not backward, sideways. It's a force that acts perpendicular to the motion. That's bizarre. Gravity pulls you down. Electrical attraction pulls you closer. But magnetism pushes you sideways, like a rude pedestrian shoving you into traffic. The standard explanation involves the right-hand rule. You hold up your hand, point your thumb, curl your fingers, and look like you're trying to hail a taxi while doing yoga. It works, but it's arbitrary. Nature doesn't have hands. Here is the truth. Magnetism is not a separate thing. It's just electricity seen from a moving perspective. Imagine a copper wire. Inside, you have positive copper ions fixed in place, and a sea of negative electrons flowing through them like a river. This is the current. Now, imagine a single negative charge moving alongside this wire at the exact same speed as the electrons inside the wire. From your perspective, standing still in the lab, you see a current. You check your rule book and it says, currents create magnetic fields. Okay? The magnetic field pushes the moving charge toward the wire. Simple. But wait. Let's look at it from the perspective of the moving charge. If you are the charge, you are looking at the electrons in the wire, and they look stationary relative to you because you're moving at the same speed. If they are stationary, there is no current. If there is no current, there is no magnetic field. So, if there is no magnetic field, the force disappears, right? The charge should drift away? Wrong. The charge still gets pushed toward the wire. But how? If the magnetic force vanished, what is pushing it?
Einstein steps in. You see, when things move, space itself contracts. It squishes. This is special relativity. From the perspective of our moving charge, the positive ions in the wire, which were stationary in the lab, are now rushing backward. Because they are moving, the distance between them shrinks. They get packed denser. Meanwhile, the electrons in the wire, which are moving with us, appear stationary. Their spacing relaxes. They spread out. Do you see what just happened? The wire, which used to be electrically neutral, now has a higher density of positive charges and a lower density of negative charges. To the moving particle, the wire has suddenly become positively charged. It's not magnetism pulling the particle in, it's good old-fashioned electric attraction. The particle sees a positively charged wire and wants to hug it. So, what we call a magnetic field in the lab is just an electric field disguised by relativity. It's what happens to electricity when you start moving. This connects back to our vector fields. We said earlier that fields define the force on a charge. We have an electric field vector and a magnetic field vector. What we just discovered is that these aren't two different actors. They are the same actor changing costumes depending on how fast you run past the stage. If you stand still, you see electricity. If you run, you see a mix of electricity and magnetism. They are components of one giant four-dimensional object, the electromagnetic field. But there is a catch. To make this work, charge has to be indestructible. Think about the conservation of charge. It's a fancy way of saying charge is conserved. You can't create electrons out of nothing, and you can't make them vanish. If a current flows out of a box, the amount of charge inside the box must go down. It's basically accounting. If charge wasn't conserved, if it could change depending on your speed, the whole universe would break. Imagine heating up a block of metal. The electrons speed up. If their charge changed because of that speed, the block would suddenly become electrically charged just because it got hot. Massive sparks would fly every time you made toast. Since your toaster doesn't kill you, usually, we know charge is an invariant scalar. It's the same number no matter how fast you go. Now, let's go back to those magnetic field lines. Remember, the divergence of the magnetic field is zero. No magnetic charges. This means magnetic field lines have to form closed loops. They are like rubber bands that never break. If you have a straight wire, the field lines circle around it. If you have a loop of wire, the field lines thread through the middle and wrap around the outside, looking like a donut. This creates the magnetic dipole. It's the basic unit of magnetism. You don't have a north pole and a south pole sitting separately. You have a loop. The north is just the side where the lines come out, and the south is where they go in. But here is a question that should bother you. Where do the lines go when they hit the end of a bar magnet? They don't stop. They go through the magnet. A permanent magnet is just a solenoid that doesn't need a battery. Inside that iron bar, billions of tiny electrons are spinning. Each spinning electron is a tiny current loop. In iron, these loops decide to line up and sing in the same choir. The result is a macroscopic magnetic field. So there is no magic magnetic fluid inside the iron. It's just currents, permanent atomic currents that never stop flowing. But we are still describing this with lines and loops. Is that what's really there? Are there invisible spaghetti strings filling the room? Of course not. The lines are just a drawing tool. What's really there is something called the vector potential. And this is where we have to abandon the high school pictures entirely and look at the machinery under the floorboards. Because it turns out the magnetic field might just be a shadow of something more fundamental, something we call A. We left off with a cliffhanger. We stripped away the magnetic field lines and realized they are just cartoons. We realized that magnetism and electricity are the same thing, just viewed from different speeds. But if we want to actually predict what the universe will do next, if we want to see the machinery under the floorboards, we need to talk about the ghost. We need to talk about A. In the simple world of electrostatics, life is easy. You have a scalar potential, voltage. It's like height on a topographic map. If you know the voltage everywhere, you just roll the ball down the hill, and that's your electric field. Simple, intuitive. But magnetism is a headache. It doesn't act like a hill. It acts like a whirlpool. It swirls. So we can't represent it with a simple scalar number like height. We need something with direction. We need a vector potential. We call it A. Think of A as the momentum of space itself. Imagine a river. The water is flowing. That flow is A. If you drop a leaf in the river, it moves with the flow. But if you stick a paddle wheel in the river, it spins. That spin, that's the magnetic field. The magnetic field B is just the turbulence that happens around the edges of the flow of A. For a long time, physicists thought A was fake. They thought it was just a bookkeeping trick, a mathematical shortcut to calculate the real magnetic field. But then quantum mechanics came along and ruined the party. It turns out you can shield a particle from the magnetic field completely, hide it behind a lead wall where the magnetic field is zero, and the particle still feels something. It feels the river of A flowing past the wall. The ghost is real. In fact, the ghost is more fundamental than the thing it haunts. The The vector potential is the primary fabric of electromagnetism. The magnetic field is just its derivative. Now I want to pivot. We've been talking about fields as if they are these ethereal, magical clouds hanging in the void. But to truly understand the vacuum, you need to stop thinking of it as a cloud. You need to think of it as a solid object. You need to go back to the jello. When engineers study solid materials, steel, concrete, rubber, they use a branch of physics called elasticity. And when we study the vacuum of empty space, we find the exact same mathematics. Consider that glob of jello we talked about. Suppose you twist it and squash it. To describe the internal torture of that jello, you can't just say it's under pressure. Pressure is too simple. It pushes everywhere equally. But in a solid, you can push on one face while pulling on another. You can twist the top while holding the bottom still. We describe this internal mess with a stress tensor. Don't let the words scare you. A tensor is just a box of numbers. If a vector is an arrow, a tensor is a machine that takes an arrow and twists it. The stress tensor tells you exactly how much force is acting on every possible surface inside the material. It tells you, on the top face, we are pushing right. On the side face, we are pulling down. And how does the material respond to this stress? It deforms. We call this strain. If a tiny speck of dust inside the jello moves from point A to point B, that's displacement. But strain is subtler. Strain measures how the neighbors of that speck moved relative to it. Did they get closer? Did they drift apart? Did they rotate around it? This is defined by the strain tensor. It's the map of the distortion. Why am I talking about engineering concepts in a script about the universe? Because energy doesn't care what it's made of. When you squeeze a spring, you store energy. When you shear a block of metal, you store energy. The amount of energy stored depends on a very simple rule. Stress times strain. How hard you push, multiplied by how much it moves. This is true for a rubber band, and it is true for the vacuum of space. An electric field is a stress. A magnetic field is a strain. The empty space between the stars is loaded with potential energy. Stored in the electromagnetic fields exactly like elastic potential energy is stored in a twisted steel beam. This is why light exists. If you kick a block of steel, a wave travels through it. We call it sound. The speed of that sound depends on two things: how stiff the material is, how hard it fights back, and how heavy it is, how hard it is to move. If you kick the vacuum, a wave travels through it. We call it light. And the speed of light? It is determined by the stiffness of the vacuum and the density of the vacuum.
You have probably seen the constants epsilon 0 and mu 0 in physics textbooks. They look like boring numbers. They are not. They are the elastic constants of the vacuum. One tells you how hard space fights back against electric stress, stiffness, and the other tells you how much magnetic inertia it has, density. Light travels at c, not because it's a cosmic speed limit imposed by the police, but because that is the speed of sound in the solid block of nothingness we call the universe. But here is where the analogy gets really fun. Real materials aren't perfect. If you pull a spring too hard, it snaps. Take a piece of blackboard chalk. If you hold the ends and pull, it snaps in half. If you look at the break, it's a clean, flat cut, perpendicular to the pull. Why? Because chalk is brittle. It is weak in tension. It cannot handle being pulled apart. But now, take another piece of chalk and twist it. It doesn't snap straight across. It breaks in a spiral at a 45-degree angle. It looks like a corkscrew. Why? You didn't pull it, you twisted it. You applied a shear. But the math of tensors reveals a secret. A shear is just a tension in disguise. When you twist the chalk, you are actually creating a line of maximum tension running at 45 degrees along the surface. The chalk finds this hidden tension and snaps exactly along that line. Nature is full of these hidden mechanisms. The geometry of the stress dictates the geometry of the failure. Does the vacuum of space have a breaking point? Can you pull on the electric field so hard that space itself snaps? In classical physics, no. But in quantum electrodynamics, yes. If you create an electric field strong enough,
a critical field. You can literally rip particles out of the vacuum. You can tear the nothing apart and create electrons and positrons out of pure stress. The vacuum isn't just a stage, it's a material that can be stressed until it breaks into matter. So, let's revisit our opening question. What exists between the object? The answer is everything. The quantum vacuum is not empty space. It is a plenum. It is a solid medium. It is a playground of fields described by vectors, scalars, and tensors. It has a temperature. It has a flow. It has stiffness. It has inertia. It has momentum. It can be twisted, sheared, and stressed. It stores energy. It carries wave. Understanding physics isn't about memorizing that gravity pulls or magnets attract. It's about learning to see the invisible scaffolding. It's about realizing that a differential equation isn't just algebra. It's a set of instructions for how the jello wobbles from 1 millimeter to the next. Einstein didn't invent a new language to describe gravity. He just borrowed the language of geology and structural engineering. He looked at the universe and realized that space-time is just a giant, bendable solid, and gravity is just the strain tensor of the cosmos. So, the next time you look at the night sky, don't see emptiness, don't see a void, see the fields, see the tensors stretching and squeezing in the dark, see the huge, invisible river of vector potential swirling around every wire and every atom. The universe is a crowded place, and the nothing is the heaviest thing in it.